Next up is to show you an example where you use conservation of energy on a problem where rotational kinetic energy is involved. So here's the example I chose. You tie a yo-yo to your finger, you tie the string to your finger and you drop it. And as you drop the yo-yo, I don't have a yo-yo here, but let me just pretend that there's a string tied around this. As this thing falls, it's going to simultaneously be falling, and as it's falling, it's going to be rotating. So it's doing both translating downwards and also spinning as it's translating downwards. So this will have both rotational kinetic energy and translational kinetic energy. So I'm already in that description doing step 1 of the conservation of energy procedure. I'm identifying what are the types of energy I'm going to need to keep track of here. And as I was just saying, I'm going to need to keep track of both translational kinetic energy, which is half mv squared, and you can call this kt if you want, and k rotational, which is half I omega squared from the spinning part of its motion. And also you're going to have gravitational potential energy, mgh, because the yo-yo is falling vertically, so its gravitational energy is also changing. Okay, next up, draw the initial and final states. So the initial state, the yo-yo is going to be up here, and it's going to be at rest because it's released from rest according to the question. Okay. So the yo-yo is there and it's at rest. The final state, it will have dropped some distance. It is now moving downwards at speed v, and also simultaneously it is rotating at angular speed omega. And don't forget, from what you know earlier in the course, because the string is tied to the outside of the yo-yo, the distance that the yo-yo drops is the same as the rotational distance along the edge of the yo-yo that it's rotating. So as a result, we can say that its rotational and translational velocities are related to each other by that formula. Okay. I also want to make sure that I define my h equals 0 reference location. I'm going to go ahead and put it at the starting location for no special reason, but I just have to put it somewhere. So I'm going to call this my h equals 0 reference level for the gravitational potential energy. And the distance that the object dropped, we'll call that d. That's what I'm solving for. And I'm going to set it up in such a way that I'm expecting d to be a positive number. Okay, so I've got my head wrapped around what the initial and final states are. The next thing is to write down the energy of the initial and final states. So for the initial state, I'm going to have kinetic energy is 0. Translational and rotational kinetic energy are both 0 because there's no motion and there's no rotational motion. And the potential energy is also 0 simply because I set that to be my h equals 0 potential energy reference level. So the total energy in the initial state is 0. Over here, the final state, maybe I'll do that over to the right. In the final state here, I'm going to have translational kinetic energy, half mv squared. Let me start plugging numbers in here. I'm going to ignore units just to make this a little bit more manageable to write. So I have half m is 2, and then v squared. V is an unknown. So this is just simply going to be v squared with the units not written. And then I have rotational kinetic energy. That's going to be half I omega squared. Now, I'm going to have a side calculation to do here before I can write this down because I don't know what the yo-yo's moment of inertia is yet. So I'll do it over in this margin here. I need to calculate the moment of inertia. So it's a solid cylinder, according to the description in the question. a solid cylinder, you can look up, has moment of inertia 1/2 mr squared. So that's going to be 1/2 times the mass is 2, the radius is 0.05. So that's simply going to be 0.05 kilogram meter squared. Okay, so I'm going to put in here 1/2 I omega square for the kinetic energy. 1/2 I is 0.05. Oh, sorry, I forgot to square it. Square, square, square. It's 1/2 times 0.05 square. That's coming from the r square in the moment of inertia formula. And then times omega square. Now, I want to put omega in terms of v so that I only have one variable. So this is going to be v over r. R is 0.05. And then this whole thing gets squared. Okay. So again, that equation there, if you didn't follow that, this is 1/2 I, and this part is omega. So that's 1/2 I omega square. So for I had to calculate using the table of moments of inertia to look up what is the moment of inertia for a uniform cylinder. And for omega, I plugged in this formula over here on the left to get rid of omega and replace it with v, so that both of my kinetic energies have the same variable, which is going to make solving it a lot easier later. Okay. Finally, I need to write my gravitational potential energy, and that's mgh. So m is 2, g is 9.8, and h, now notice that h is below my reference level, so I'm going to need a negative sign there if I want the variable d to come out as positive. So it's d below my h equals 0 reference level. And 2 times 9.8, let me just make sure I do it right, is 19.6. Yeah. Minus 19.6 times d. Okay. And by the way, in the rotational kinetic energy formula, I didn't actually say this, but if you didn't notice, it actually turns out that these two r's cancel out because they're both 0.05 squared. So that ends up just being 1/2 v squared. So then finally, if I add all of these together, the energy in the final state ends up being v squared for the translational kinetic, 1/2 v squared for the rotational kinetic, and minus 19.6 d for the potential. And the initial energy was just 0, remember. So then when I apply conservation of energy, I set initial equal to final. Let me just change pen color so that it doesn't get too cluttered. So I'm going to set initial energy equal to final energy. So that's going to be 0 equals 1 plus 1/2 is 3/2. So 3/2 v squared minus 19.6 d. And v was actually given in the question, I guess. I forgot to plug that in. V is actually 2.5. So I'll have 19.6 d equals 3/2 times 2.5 squared, which gives me d equals, so I'm going to have 3 divided by 2 times 2.5 squared divided by 19.6, and that gives me 0.48 meters. And again, that means 0.48 meters below where I dropped it from. And that's my final answer. So notice the problems are starting to get a little bit more complicated now that there's multiple different types of energy involved, but the procedure remains the same. You just write down each individual type of energy for the initial state and the final state. You add them all up, and then you set it equal in the initial and the final state to apply conservation of energy.